The universe is a realm of endless wonders. It's a place where certainty often eludes us. From the smallest subatomic particles to the grandest cosmic structures, randomness plays a fundamental role. In our quest to understand the universe and its intricate workings, we turn to the power of statistics. Statistics provide us with the tools to make sense of the unpredictable. It helps us navigate the realm of chance and probability. At the heart of this statistical framework lies the concept of random variables. Imagine flipping a coin. What will the outcome be, heads or tails? The answer, of course, is uncertain. The outcome of a coin flip is a random event. Now, imagine rolling a six-sided die. What number will appear on the top face? Again, the answer is uncertain. Each face has an equal chance of showing up. These simple examples illustrate the essence of random variables. A random variable is a variable whose value is a numerical outcome of a random phenomenon. In the realm of statistics, we seek to quantify the unpredictable. We strive to assign numbers to random events, making them measurable and analyzable. This is where random variables come into play. Random variables allow us to bridge the gap between the abstract concept of randomness and the concrete world of numbers. By assigning numerical values to the outcomes of random events, we can apply the tools of mathematics and statistics to understand and predict their behavior. Let's revisit our previous examples to solidify our understanding of random variables. Random variables are fundamental concepts in probability and statistics, and understanding them deeply can help us in various fields such as data science, economics, and engineering. When flipping a coin, we can define a random variable, let's call it X, to represent the outcome. This outcome can be either heads or tails, and we can quantify these outcomes using numbers. We can assign the value of 1 to heads and 0 to tails. This assignment helps us to use mathematical tools to analyze the outcomes. Now, X becomes a random variable that can take on the values of 0 or 1, each with a probability of 1/2. This means that if we flip the coin many times, we expect heads to come up about half the time and tails the other half. Similarly, when rolling a die, we can define another random variable, let's call it Y, to represent the number that appears on the top face. Unlike the coin, a die has 6 faces, so the random variable Y can take on more values. Y can take on the values 1, 2, 3, 4, 5, or 6 each with a probability of 1/6. This means that each number has an equal chance of appearing on the top face when the die is rolled. Understanding these probabilities helps us to predict outcomes and make informed decisions based on the likelihood of different events. By using these simple examples of a coin flip and a die roll, we can build a foundation for more complex random variables and probability distributions. These concepts are not just theoretical, they have practical applications in real-world scenarios. For instance, data analysts use random variables to model uncertainties in data, helping businesses to make data-driven decisions. Engineers use them to assess risks and reliability in systems. Economists use them to model market behaviors and forecast economic trends. As we continue to explore random variables, remember that these basic principles are the building blocks for understanding more advanced topics. Keep practicing with different examples, and soon, you'll be able to apply these concepts to a wide range of problems. So, let's keep learning and exploring the fascinating world of random variables and probability. The more we understand, the better equipped we are to tackle challenges and make informed decisions in our personal and professional lives. Section 5. Discrete versus continuous, a fundamental distinction. Random variables come in 2 main flavors, discrete and continuous. This distinction is crucial for understanding their properties and how we analyze them statistically. Discrete random variables, as the name suggests, take on distinct, separate values. These values are often integers, but they can also be a finite set of non-integer values. The key characteristic is that there are gaps between the possible values. Section 6. Delving into discrete random variables. Let's delve deeper into the world of discrete random variables. These are variables that can take on a countable number of distinct values. They are often used in scenarios where outcomes are finite and distinct. Imagine flipping a coin 3 times. Each flip has 2 possible outcomes, heads or tails. The number of heads we get can be 0, 1, 2, or 3. Each of these outcomes is a discrete value. This is a classic example of a discrete random variable. The outcomes are countable and there are no intermediate values. The possible values are distinct and finite. This means that between any two values, there are no other possible values. There are no values between 0 and 1, 1 and 2, and so on. This is a key characteristic of discrete random variables. Another example is the number of cars passing a certain point on a highway in an hour. Each car that passes is counted as a whole number. The number of cars can be 0, 1, 2, and so on. Each count is a discrete value, but it cannot be a fraction like 1.5. Discrete random variables are always whole numbers. Another common example is rolling a die. The possible outcomes are 1, 2, 3, 4, 5, or 6. Each outcome is a distinct, countable value. Discrete random variables are often used in probability and statistics to model real-world scenarios where outcomes are limited and distinct. They help us understand the likelihood of different outcomes and make predictions based on data. By studying discrete random variables, we can gain insights into various phenomena and make informed decisions. In summary, discrete random variables are a fundamental concept in statistics, providing a way to model and analyze situations with distinct, countable outcomes. Understanding them is crucial for anyone studying probability, statistics, or any field that relies on data analysis. So, as we continue our journey through statistics, keep in mind the importance of discrete random variables and how they help us make sense of the world around us. Section 7. Exploring continuous random variables. On the other hand, continuous random variables can take on any value within a given range. Imagine measuring the height of a student. The height can fall anywhere within a certain interval. It's not limited to specific, predetermined values. Other examples include temperature, weight, and time. These variables can take on an infinite number of values within a given range. Section 8. Probability distributions mapping the randomness. In this section, we delve into the fascinating world of probability distributions, which are essential for understanding the behavior of random variables. Every random variable has a probability distribution associated with it. This distribution provides a comprehensive way to describe the randomness and variability inherent in the variable. A probability distribution is a function that describes the likelihood of obtaining the possible values that the random variable can take. It essentially maps out the probabilities of all potential outcomes, giving us a clearer picture of what to expect. For discrete random variables, we use probability mass functions, or PMFs. These functions are particularly useful when dealing with variables that can take on a finite or countable number of values. PMFs assign a probability to each possible value of the random variable. This means that for each possible outcome, there is a specific probability that quantifies how likely that outcome is. For continuous random variables, we use probability density functions, or PDFs. Unlike discrete variables, continuous variables can take on an infinite number of values within a given range. PDFs describe the relative likelihood of the variable falling within a particular range of values. The area under the curve of a PDF represents the probability of the variable falling within that range, providing a powerful tool for analyzing continuous data. Understanding these concepts is crucial for fields such as statistics, data science, and any domain that relies on data analysis. By mastering probability distributions, we can make more informed decisions and predictions based on the data we observe. Section 9. The importance of random variables in statistics. Random variables are the building blocks of statistical inference. They allow us to make inferences about populations based on samples. By understanding the properties of random variables and their distributions, we can develop statistical models to test hypotheses, estimate parameters, and make predictions about future outcomes. Section 10. Conclusion. Embracing the unpredictable. In a universe where randomness reigns supreme, random variables provide us with a powerful tool to navigate the unknown. By embracing the uncertainty inherent in random events, we can use statistics to gain valuable insights into the world around us. Whether we are analyzing data from scientific experiments, financial markets, or social surveys, random variables are essential for understanding the patterns and relationships that shape our world.